main complications of diabetes is that it affects our eye. It starts causing damages to our blood vessels, and these are the light sensitive blood vessels in the back of our cornea. So when these blood vessels starts clogging up, our visibility starts to diminish. The problem is that at first, diabetic retinopathy starts to seem like just like normal eye wear. So people normally go to an optician and get glasses, but that doesn't really cure it. And due to this, if it gets into the advanced stage, it is very difficult to cure, and sometimes it can even lead to blindness. So challenging this, detecting this is a huge challenge. Now, there are mainly two types of diabetes, diabetic retinopathy. Early diabetic retinopathy, this is also called non-proliferative diabetic retinopathy, and advanced diabetic retinopathy, which is called proliferative diabetic retinopathy. Now, there also has been a Kaggle competition, which is called APTOS 2019 blindness detection. This competition was created for this particular purpose only, that we solve this problem of diabetic retinopathy using artificial intelligence. The link for that competition is given in the collab notebook. The main challenge in this data set is that the data is very heavily unbalanced. So as you can see, class 0, which is the first primary class of data in which there is no diabetic retinopathy, this compromises of almost half of our samples, 49.29% to be exact. Class 1, which is the case of mild diabetic retinopathy, that accounts for 10%. Class 2, which is moderate diabetic retinopathy, this accounts for 27.28%, so almost 30%. Class 3 is severe diabetic retinopathy, which is only 5%. So these classes 1, 2, and 3, they belong to the early diabetic retinopathy stage, which is the non-proliferative diabetic retinopathy. Then we have, of course, our fourth stage, which is the proliferative diabetic retinopathy. And this is where things get really, really serious. At this point, there may or may not even be a cure. So, using this data set, the best approach which we had, the best success that we had using a DesNet 152 architecture was about 70% accuracy with 0.62 kappa. Now, what we are going to do is we are going to provide you a balanced data set. So remember, the data set that originally we had is an unbalanced data set. What we will be using in our experiment today is a balanced data set which has been randomly sampled, so that you get a balanced field and you can start your experiments without worrying too much about the data set. Now, if you click on the drive folder, you will be redirected to a drive of this diabetic retinopathy, in which we have the data and the dataset description, and as well as the problem set description. Uh, Ravi, could you head over to Google Drive? Inside Google Drive, you'll find this. Click on the drive data back in the Google Colab notebook. Click on drive folder. If you click on drive folder, you will be redirected to this the balanced data of retinopathy. Now, inside this, right click on the balanced data retinopathy and make a copy. When you do that and you do on your show file location, this will make a copy of the data set in your Google Drive. Now, this is important because then we can use this data directly in our Colab notebook. Uh, Coming back to the Colab notebook, Once you do that, and once you mount your Google Drive, now you need to mount your Google Drive from your Collab notebook. So for that, go to your left hand side and click on the folder icon. And inside this, there is a button for mounting your Google Drive. So click on that button, that one. Now inside this, it will paste a code in your cell. Just run that cell. Go to that cell and press Shift Enter. Run that cell again. Run anyway. Connect to Google Drive. Now, once you do that, you'll have your Google Drive mounted in your Collab notebook. And as you can see, the drive is mounted. So now, if you go and refresh your files, uh, no, in the Collab notebook itself. Yep. Now you can see that your drive has been mounted on your files folder. Now go to your drive, click on your drive, and find the balance data which we had on this. On go to my drive. Yeah, that copy of balance data. Now copy its path. Okay. Now scroll down on the Collab notebook. Little bit up on the first cell itself. I hope everyone is following me as I am explaining to them. If you want, if I'm going too fast, you can just tell me to wait and I'll hold on. Scroll up. Go to the first cell on which we are extracting data. Below the cell behind building model on next cell. Next. Yeah, here. Now inside this, in the tar minus xdf, now delete the path which was existing there and paste the path that we have just copied and run this cell. I think we need to rename that folder, rename that file, and then copy the path again. Linux does not support spaces. So as you can see, it has started to copy the images or extract the images into this balanced data folder. So here, what we have is we have 193 images from each of the 5 classes. So there are a total of 5 classes: 0, 1, 2, 3, 4, where 0 represents no diabetic retinopathy. 1, 2, and 3 represents the 3 levels of early diabetic retinopathy, and 4 represents the final stage, which is the proliferative diabetic retinopathy. Now, here what we will do is we will take this data, clean it, and build it into residual network classifier so that we can detect diabetic retinopathy. Okay. Now that we have extracted our data, our next step is to clean up the code. So first we will import pandas, and then we will read the class labels. So these labels are the files which contain the image name and the label which comes with them. Now, from your supervised learning examples, you have known that to train any supervised learning models, we need data with their labels. So we need to tell that, okay, this image is from class 1, this image is from class 2, this image is from class 3. So those that map is contained in this class 0, class 1, class 2 CSV file, and we are going to read those. So in order to read those, we need to first import pandas, run the cell with import pandas, and then we need to read all those CSV files. So run the cell with those CSV files. Now after this, we can just check the shape of any random data frame. So here we are checking the shape of label underscore 2. Run that cell. No, first you need to run label.2.shape. The one above it. Yes. The one above it. Labels underscore 2.shape. Yes. And then what we need to do is we need to, okay, now we have these 5 data frames: label 0, label 1, label 2, label 3, label 4. So now we need to add these 5 data frames into one single data frame. That is why what we are doing in that line. Labels is equal to pd.concat label 0, 1, 2, 3, 4. So run that line. Uh, no, the one below it, and the one below it. Yes, this one. Now, once this is run, then we can our all these 5 files are combined into one single file, which is called labels. Now let's just check the head file of it. So run labels.head. So now you can see that, okay, these are the labels that we have. Now after this, what we need to do is still the file that we have. This has first 193 files of class 0, then the next 193 files of class 1, then the next 193 files of class 2, so on till class 4. So what we need to do is we need to shuffle up the deck. So for that, first we need to from import train test split from sklearn. So we need to execute that line from sklearn.model selection import train test split. Run this one. Now we need to split our labels into the training and the testing set. So now you can just train set underscore test, yeah, run that line. So now what train test split will do is it will take all the examples in labels, shuffle them up like we shuffle a deck of cards, and then distribute it into 2 sets: the training set and the testing set, where the size of the training set will be 80% of the data, and the size of the testing set will be 20% of the data. This is specified in the test size parameter, the one that we have passed. So now if you can just check the shape of training set, so we can execute train underscore set dot shape. So this has 772 examples. The rest, 193 examples are stored in test shape. Now after this, we have to still the images that we have, they are in the same .png format that the images came in. But our model cannot process that. So right now, what we need to do is we need to take the image and then process it so that it can be consumed by a AI model. For that, we need to apply some transformations on the image. Now, what these transformations will do is that if you can closely see in the transforms list, it has first transforms dot resized crop. Now, what this will do is it will take any random 224 by 224 patch of the image and it will send that sample to the data loader. So this way, every time that you run this model, you'll get a look in a new portion of the image. This is necessary so that our model does not memorize any pattern, it actually learns from it. So you know the difference between memorizing and learning. That's what we are trying to avoid here. That our model does not memorizes anything; it actually learns from it. So what we are doing is every time that our model will look at the data, we want it to look into a new patch of data. So the first part will what it will do is it will take a random crop of the image, which is of 224 by 224 bytes. Similarly, it will flip it horizontally to some times depending upon some random factor. Then it will convert it into a tensor and then it will normalize it. So this way, the image, the PNG image that we have is then transformed into a appropriate mm, tensor of numbers, which can then be processed by our machine learning model. Now, please run this cell. Now, here we are using Torch, which is the PyTorch library used for deep learning. In the next cell, we already have our data directory. So we have just specified the data directory in a the path of the data directory. So run this cell. Data directory is equal to content underscore balance data. Now after this, just so that okay, we can access the image paths and the image files. We are just going to check okay what is in a single sample of the train set. Any random sample would do. So then the next cell name underscore label is equal to train set 27. I love 27. Now next what we are going to do is we are going to create our data loader. Now our data loader is a class which will take the data set that we have provided. So basically right now at this point we are providing it with just two things. The folder which contains the images and the mapping, a CSV mapping of the file name with the class. Now we need a class which actually reads the image, applies the transformations, and then sends back the tuple which contains the tensor and the class label. Now, the tensor is the processed form of data. So it is just a funny way of calling data, but it will have much more huge implications because tensors are a kind of data structure which are heavily optimized to run in CPUs as well as GPUs. So we need to clean the data and we need to transform it into a tensor so that it can then we can be used or for processing in a GPU. So here in so here in our class diabetic retinopathy dataset, what we are doing is we are providing it with a data set. That data set is a path for the entire directory of data. So what we are looking here is data directory is the directory which contains all the images. Data df contains the file which contains the mapping from image to the class image mapping. That is the data df, which will be a data frame. Transform are the transformations which we will provide, and the ext is the extension of the image. So images can be JPEG or .png. So accordingly, we need to because we have to read the. So after this, we are just these to the class data frame here. So cell data df, cell dot data directory. These two methods are important. Return the length of the dataset of all the samples that are in the data. The get item method. The get item uh, the code, and then it process the image with the transformation and then sends back them. Come to the get dataset class. We are okay. I think we are having problems from connecting data from drive. Okay. Let's repeat the process. Ravi, can you scroll back up to the point where we mounted Google Drive? Scroll up, keep scrolling up. A little bit up, more point from the point on which we have the data folder link, data folder. So the first step is that click on the data folder. Now this will take you to the diabetic retinopathy dataset folder, which has three files. Now in this, you have a balanced data underscore retinopathy. Then we have your diabetic retinopathy PDF, and then you have your train.csv file. Now here I want you to copy the balanced data file. So right click on the balanced data and click on make a copy. Make a copy. Now what this will do is this will take the data set from here and copy it into your drive. Right now this is in my drive, which I've shared with you. When you make a copy, this will copy this and it will put it in your drive. So click on make a copy. Now when you come to your drive, uh, open up your drive folder. Now inside this, you'll have this copy of balance data. Okay. Now right click and rename it. Now rename it without using spaces. So remove the spaces and you can put a number also. Okay. Now once you have renamed this to balance data underscore retinopathy, go back to your Google Colab. Go back to your Google Colab notebook. Now inside this, you scroll down and first you need to connect your drive with your Colab notebook. So first that on your left hand side, click on the folder option and then click on the Google Colab drive mount. Now once you have click on that, now once you run that cell, this will paste some code in that cell. Once you run that cell, this will ask you for some authentication process, and it will mount the drive. If the drive is already mounted, it will show the drive already mounted at content.drive. Now, after that, I want you to go again back to the left hand side on the file explorer. And there, I want you to locate the balance data retinopathy file that we had. And then copy its path. Now, after that, I want you to paste this path in the tar -xvf command cell. So here, what you have here, this I want you to remove this path and place your path here. Now, once you have pasted this, run this cell. Now, once you do this, this will extract everything in the balance data folder, which will be inside your content folder, and the rest of the cells you can execute accordingly. Now, coming back to the dataset class, please scroll down to the dataset class. Now, inside this dataset class, we have the main function, which is the get item function. Now, inside this get item function, here we are doing three very important things. First is that from the data frame that we provided, which contained the image name and the class name, we are getting both the image name as well as the class name, which we are associating with the name label here, the first line of that. After that, we are combining this name with the path of the directory and the extension, and then we are opening this image. So we have the now that we have the complete path, we are opening this image, and then we are using this image and applying the transformations which we have created earlier. So those transformations are applied on that image, and then that image is being returned with the label. So the image that it is being returned from the label, this image is in tensor form, the form that we took about. Now, if you scroll down in the next cell, what we are doing is we are creating a dictionary of datasets. So dataset train will contain the dataset for the training label or the training portion of the data, and the dataset val will contain the dataset of the validation portion of the data. After this, this is the dataset class. So this is a specific PyTorch class for handling datasets. After that, we need a data loader class. This data loader will contain the training and validation data loaders, and this data loaders are also important. Now, in PyTorch, the, the data pipeline consists of these two critical components, the dataset and the data loader. Now, what the dataset will contain is how you are opening your data, how you are where the data is located, how you will read your data, what kind of transformation we will provide in your data. That all that thing is being taken care of in your dataset class. The data loader class will tell your model how many such pipelines to build. So suppose that here we are using a batch size of 4. This implies that we want each batch size or each chunk of data to contain 4 images. We can change that into let's say 8 or 16 or 32, depending upon your machine size or how much your machine can handle. So if sometime you run out of a memory, you can just simply decrease the number of batch sizes and it will work smoothly. After this, we are creating a dictionary for the dataset sizes, and then coming to the next line, which is device is equal to torch.device. This is an interesting one. Ravi, scroll down, please. Okay. Torch is device is equal to torch.device CUDA 0 if torch.CUDA is available, else CPU. Now, like I told you, we need specific GPUs for processing image data. In GPUs, it works really fast. Imagine this: a CPU has typically 8 cores. If you are very lucky or very rich, you might have something with 16 or 32 cores, but that's it for a CPU. Whereas a GPU, on the other hand, may have 2,000 to 4,000 cores. So, using this advantage, systems with NVIDIA GPUs and NVIDIA GPUs only can process machine learning tasks on GPU. Now, for that, if our device has a GPU, we need to push the data from CPU to the GPU, which is being done using this command. Now, this command, what it will do is, it will take the device flag and set it to CUDA colon 0 if we have a GPU, or it will set it to CPU if there is no GPU. Now, luckily, Colab provides us with the Tesla T4 GPU for free, so we can use the GPU power here. Now, after this, I am going to create a function for displaying the images in the cell. So here, whatever we did in the dataset class, we will do the exact reverse of it. So for instance, like we had normalized the image, so we are going to denormalize it, which is why we want to calculate the mean and the standard deviation of the image, and then we want to denormalize it. So which is happening in the input is equal to standard multiplied by input plus mean, which is the reversal of the normalization process, and then we are going to return the image. So the IM show, what it will do is it will take the tensor which has been processed data set for an image, and it will reverse the processing that we have done to give us an image. And then our out is equal to torchvision.utils.make grid inputs. What it will do is it will take a grid of that image and it will display it. Ravi, run this cell, please. Oh, no, no. For that, you have to run the beginning previous cells also. To start from the dataset class, yeah. Okay. So here we have just verified two things. Number one, that okay, our normalization and denormalization process works because we have normalized it at one end and denormalized it at the other and displayed the image. And second, our batch loader and the batch sizes work. Now scroll up to the data loader class where we had created the data loaders. Yeah, there. Uh, Scroll down below on cell number 21. Okay, in this, convert the batch size from 4 to 16. And the above one also. Yeah, above in the training set also. Just above in the above line. And then run all the cells from this one and the below it. Run this in the cells below. So as you can see now, instead of 4, we have these 16 images, which are stacked on these two rows. Now, as you can see, these are the images which are being used for classification. So let's go and let's start with our classifier model. So first we have some imports on the cell below. Run those imports. Now after this, we need a method to train our model. So this is where the train model comes in. Now forget the parameters for a moment and just let's go in the main training loop. Now what it is doing is, if the phase of training, now each training pass has two phases, the training pass and the validation pass. So if the phase is in training, it will set the model.train flag. Otherwise, if the training is in a, if the pass is in evaluation mode, it will set the model.evaluation flag. Now after this, for inputs and labels in data loader. So here we are receiving the data from the data loader. Input.to device, labels.to device. What this line is doing is, if we have GPU available, it will take the data and push it to the GPU. Otherwise, it will process it at the CPU. After that, we are uh, resetting the optimizer. So optimizer is the function which trains the network. Here, optimizer is the function which trains the network. So what it will do is it will take all the previous training gradients and will reset it to zero. After this, if it is training mode, so we need to learn from it. So set grad enable. This flag is set true in training mode, and then we pass the input through the model, and then we calculate the loss in loss is equal to criterion output dot labels. So criterion is the function which calculates how much loss has been occurred in this prediction, and if the model is in training mode, that loss is propagated backwards to learn, and then our optimizer is asked to update the weights. So this is how the training loop works. So for each example, it will take that example, pass it through the network, and get a result. Then it will use a function called criteria, which is a function which we will have to pass to the network. It will use that function to calculate, okay, what kind of losses did we incur here, and based on that loss, it will optimize the network through a function called optimizer. Again, optimizer is also a function which we will have to pass here. Now, the mathematics behind the criterion optimizers is quite complex, so we will let it for our another session. But in short, what it is doing is in a forward pass, it is taking an image and making a prediction. Then it is making that prediction, matching that prediction to the actual result, and then calculating, okay, whether this prediction is accurate or whether it is inaccurate. If so, how much inaccurate? Based on that, it is calculating a loss, and then it is propagating that loss backwards to the network so that the network can learn itself, so that in the next pass it will make lesser mistake and it will try to improve the network. But this, all of this pass is done only in the train phase. So this is why we need to put the flags where if it is training phase, then optimize the network. If it is validation phase, do not optimize the network. So this is the loop here. After this, below we have our total epoch loss. So one epoch is basically one iteration of the loop. For some historical reasons, it is called epoch. Now after that, we want to save the best weights of our network, correct? So what we want to do is the model with the best accuracy, we want to return that model to, we want to return the weights of that model so that we can use it to make a prediction. On this part, we have to check phases validation and if our current epoch accuracy is greater than our best accuracy. If so, then we want the model and go forward. Ravi, if start running the results, port, scroll up. Yeah, and from the import, execute on, hold on. Loop. So we still need to provide network model with a criterion function with a and with a scheduler function. We need a model. So I'm going to use a model called Resonate 18. Is a Resonate 18 is a convolutional neural uses residual connections in its network, and it has performed excellent in the results for computer vision tasks. I have shared a link with the link about the description section, so you can go ahead and about those here. We are going a network which has already been network, and then that model on our data. You see the first line, model to models.resonate 18. What this line is doing is this line is down called resonate 18 model. It When I say download, it means that we are downloading the data set from our particle problem. Am I audible? Is my voice audible? Okay. Okay. So I'll repeat this cell again. Model underscore ft is equal to model dot resonate 18 pretend equal to true. This first line of this cell, what it is doing is this is taking a downloaded model of resonate 18. So this is a pre-trained model of resonate 18, and it is downloading that model. Now, after this, we need to customize this model for our particle problem. So, as you know, a neural network has many layers of neurons attached in a network fashion. So, in this, what we are going to do is we are first taking the last layer of the current network, and we are putting it another layer on top of that, and then we are mapping the top layer to the number of classes that we have. So as you can see here, number of features, this contains the outgoing feature of the current network, and then we are mapping this to the number of classes that we have. Since we have 5 classes, we are mapping it here. Model underscore ft.fc is equal to nn dot linear num features comma 5. So here we are mapping it to the 5 filters here. And then again, we are pushing this model underscore ft is equal to model underscore ft dot to device. So we are pushing this network back to the device, which is GPU or CPU, depending upon whatever our device is. Now, after that, we have the criteria. So this is the criteria file which calculates the loss. So here we are using cross entropy loss. After this, we have the optimizer function. Now, this is the function which will optimize the whole network. This is the function which causes the main learning part here. So this here we are using the optimizer function, and then we are going to use a linear learning rate scheduler. So what it will do is, as we learn more and more, we want our learning rate to decrease slowly, so that we can learn the finer details of the problem. So we want to learn very fast at the beginning, and then we want to slow our learning pace as we go along. So this comes in the expert LR scheduler. Now, Ravi, please run this cell. Okay. Now, this cell starts the actual training process in which we are passing the model underscore ft, the criterion, the optimizer, the expert LR scheduler, and the number of epochs. So here we are training it for 5 epochs. So now all of this that we have created, the data pipelines, the training network, the criterion, the optimizer, the learning rate scheduler, and we are pushing it to the trained model loop function which we created in the training network. So what it will do is it will take an image, pass it through the training model loop, and then again it will take the output of that image, uh, give it to the loss function. It will calculate the loss, give it to the optimizer function, get the optimizer gradients, and then pass those optimizer gradients back along to the network so that the network can learn. This is deep learning, guys. So now, if you'll wait for a little bit of time, this will start showing some results, and this usually takes some time, approximately 5-10 minutes to train itself. If you have any questions, you can start asking questions at this point. Now, once the training is complete, this will return the trained model back to you, and which will be saved in model.tree. So here we can see that, okay, we already have our first epoch in which the training loss was 1.49 and the accuracy was 0.33. So here 0.33 means that it, the accurate. Now, as you can see, this is quite low. It goes on to about 50-60% in this configuration. So for that, our what I would say is that your task after this session is to replicate this entire process and go through the cells. Once you have executed this entire collab notebook, you can then contact Ravi and we can start with the next part of the process on developing this project. If you have any questions, we can start with the questions now. If you want to ask questions, you can either speak or you can put the question in the chat section. Okay, so you want a brief introduction of the green part. Okay. Ravi, can you scroll up at the absolute beginning? Okay. So this problem statement is about detecting diabetic retinopathy, which is a complication which arises due to diabetes. Now, in this, there are two or three main problems. Number one is that the image that it is used to detect diabetic retinopathy, this image comes from a very specialized camera called fundus cameras, and they take images of our retina. So detecting diabetic retinopathy for is a very skilled task which requires skilled hardware and an equally skilled expert doctor, which is unavailable in most areas. So what we are trying to do here is we are trying to take a trained data set of diabetic retinopathy images, and we are trying to build a classifier which can detect diabetic retinopathy by using the image. For the data set, we are using the data set from the Kaggle competition APTOS 2019 blindness detection. And this data set is a heavily unbalanced data set of 5 classes. The class distributions are shown in the challenges section. Now, in this, you have these 5 classes in which the class 0 is of no diabetic retinopathy. Class 1, 2, and 3 are the mild, moderate, and severe category of early diabetic retinopathy. And class 4 is the proliferative case of the advanced diabetic retinopathy. Now, the data description, all this is shared in the drive folder, the link of which is provided here. If you scroll down, we are using, hold on, just here. We are using residual neural networks, which are a type of convolutional neural networks for this process to build our first model. Uh, the research paper for residual neural networks are provided in the link. You can go ahead and read about it. For this, we are using ResNet 18 model, which is trained on the ImageNet dataset. Now, this is just a introduction to the problem. Once you get familiar with it, we will try even more advanced architectures on this. So this session is just to introduce the problem to you and give you understanding of what you can do. So the next step from this point forward is to try different architectures and improve the accuracy even further. Now, my target is to reach 95% quadratic kappa so that it can accurately detect whether an image has diabetic retinopathy or not for 95% of the times. So that is the target that I am working on. Right now, I am at about 70%, and this model that we have built in this example reaches about 60%. So we can see that, okay, there is a lot of ground to cover. Even the competition itself gave it to around 85-86% only. So this is the part that we are doing. All the code and all the experimental data that you will need is provided in this collab notebook itself. The collab notebook has been shared with you. The recordings of the session will be shared with you. Those people who have executed this program either in this session or in the weekend period of this, please contact Ravi on Monday. Those who are interested in taking this project forward, please contact Ravi on Monday. We can start the next steps of the process from Monday onwards. Do we have any more questions? Okay, what is the next step after completing this execution? Please contact Ravi and let him know that you are interested in working in this project. The next steps will be provided to you on Monday for this project.
Thank you, sir.
Ravi, can you scroll down to the results? To the absolute last, the results. Okay. So as you can see, the third epoch, which is 2 out of 4, we have reached around 56% accuracy in the validation phase. So this is quite decent considering that our model has only 18 layers. It's Resonate 18. So considering that we have only used a very small model and that too pre-trained, this is giving us quite decent result. But okay, Nikita's question is basic Python enough for proceeding for this project? Yes, but you will have to learn a lot for in the part of deep learning and all. You'll have to learn quite a bit. Basic Python will get you rolling, but you'll have to learn deep learning as well. We will teach you about that. Don't worry. So as you can see that this has reached around 56% accuracy in what is 10 minutes 6 seconds. Yes. So in around 10 minutes of training and 10 minutes of training on a GPU, we have achieved around 56% accuracy. Actually, this part gets our hopes up that okay, if we use a bigger data set or we use a bigger network or if we train for a longer duration, we might achieve 95% accuracy. But this is where this problem clean bolts us. At around 60 to 70%, maybe 70%, this gets plateaued. So no matter how much resources you throw at this problem, it does not improve any further. So it is bottlenecked at 70%. You need to find ways, or rather, we need to find ways to break that bottleneck and increase the training accuracy and the testing accuracy. Our ultimate objective will be to create a software which can detect diabetic retinopathy with medical precision. Okay, guys, so this will be all for today's session. Ravi, would you like to add anything?
No, no, that's all.
Okay, guys, thank you very much for joining. Those who are interested in executing this process, executing this project forward, please contact Ravi through the Hexart official group. Thank you all. Thank you, guys.
Thank you.